Hi, this is the little bit of explanation of the simplex method, and it's intended to give like a more concrete version of what's going on in the pre-reading in pages 65 to 66. So there's a very precise mathematical statement of how the simplex method actually works, given some of our previous work, and so we want to do simply jump in and do embedded exercise 39 and explain, kind of connect that to all the theoretical discussion on page 65 and 66. So the first thing I have to do is bring in the little tableau for embedded exercise 39. Okay, there we go. Just kind of put this up here. We have some room to write. Oops. Okay, so this is a typical simplex tableau, and we're sitting in a situation currently where the basic variables are these. So this is the so-called, in the theory, XB. So the basic variables are x2, x4, x5, and x7, and so they actually have values. So currently, z is equal to something, the function value, which is probably 28, but the, well, yeah, that is true. So notice that currently x1 is 0, x2, as you can see, this equation says that x2 equals 1. So, and x3 is non-basic, so it's held at 0. x4 is currently 4. And x5 is currently 2. x6 is a non-basic at 0, and x7 is equal to 3. Now each of those facts about the basic variables follow very simply. For example, for x4, it's the bottom row equation says 0z plus 6x1, but x1 is 0, so that's ignorable. And then with 0, x2 plus 8 times a 0 variable, and so on. So the zeros disappear, and the only thing we get is 1 times x4. So this whole row just ends up saying x4 equals 4. So the basic variables are very easy in that way. And the top row says that z, and just like we just did, the basic variables, the basic variables, non-basic variables are the only ones that can have a non-zero, and they're all equal to 0. And the in all the basic columns we have zeros because of the pivoting, the raw operations we did. So that just says that xz equals 28. But now we want to move to an adjacent extreme point. So an extreme point, or a corner point, is the whole point of the simplex method. It goes from extreme point to extreme point, getting better and better scores until it finds the best one where it can't improve any. So how do we do that? The whole idea is to pick a non-basic with a negative reduced cost. So that's just reduced cost is the fancy term for this hideous formula we had for the top row. But all it amounts to is there's two candidates here. X3 and X6 are two non-basic variables that could profitably be allowed to become basic. And we can see that by just saying let X3 become alpha, which is some positive number. So we're just alpha is a parameter we're going to play with and just see what happens. So if we rewrite the top equation, it says 1 times z, and again it's 2 times x1 is being held at 0, so that doesn't contribute anything. Oops. X2 is multiplied by 0, so that doesn't contribute. So finally, then we get the plus the negative 3 times the value of x3, which is alpha. And then 0, 0, and then minus 2 times a variable that's still being held at 0, x6 plus 0. So we just get this equation. And with a little bit of algebra, we find out that the objective function value z is equal to 28 plus 3 alpha. So increasing alpha improves the objective function z. So that's great. And we think we're in great shape here. And we are. So every unit of that we increase alpha by, so if we increase alpha to 1, z would go to 31. And alpha to 2, z would go to 34, and so on. So every 1 unit increase in alpha increases z by 34. So does z go to infinity? And it would if we didn't have some constraints. So the answer is no. The constraints get in the way. So the constraints stop it. So we're now ready to look at the constraints. And to look at the constraints, I'm going to change colors. So these numbers are crucial. So we've got the right-hand, the column, and the right-hand side. So we can now write down what the equations say. And I think I'm going to roll this whole thing up a little. Oops, that didn't work. I've got to have the magic hand. So I'm going to roll this up to where we have a little bit more room to write. Okay, so let's just look at what the equations say. So the equation for x7 says, all right, I think I'll stick to red, because why not? No, it's probably no point. So the row, this row, the first real constraint row, again, it's 0z minus 3 times x, a value being held at 0, plus 0. So all it ends up saying is 12x3, but we're assuming x3 is alpha. And then we get 0, 0, 0, and 1 times. So notice x7 is in there, of course, because this is the row for x7 that x7 is basic variable for. So we end up with this fact. So that equation, if we allow this guy to sneak up to alpha, that just simply says 12 alpha. So there's 12 alpha plus x7 equals 3. And now if we fiddle with that, we want to put that in terms of what it says about alpha. So alpha is equal to 3, oops, sorry, never mind. So we want to solve for x7. What does this say about x7? It says x7 is equal to 3 minus 12 alpha. So how big can alpha? And with the restriction says x7 is bigger than or equal to 0. So back here when I said the constraints stop us from increasing alpha forever, the more accurate is the constraints plus the restrictions. So it's the fact that x7 can't go negative that's stopping this. So this equation, that 3 minus 12 alpha is bigger than or equal to 0, says 3 is bigger than or equal to 12 alpha. And that says alpha is less than or equal to 3 over 12, which is 1/4. So this is an upper bound on how big alpha can be. And that upper bound is simply this number divided by this number. So in the notes, in the theoretical description, this is called R sub I and this is called U sub I. But it's a very simple idea if you do it with actual numbers. Okay, so we can't increase alpha any more than 4. Is that right? Yes, it is. Okay, to 1/4 rather. Okay, the second constraint for x2, the equation says, so x1 is so 0, non-basic, so we get 5 times alpha, the value of x3, is the basic, and the only, oops, I missed it. So where is it? Oh, x2, yeah, I skipped right over it. So this actually says in order that x2 plus 5 alpha equals 1. So we'll switch that around a little. And so that says that x2 is equal to 1 minus 5 alpha, which says x2, and to say that's bigger than or equal to 0, says that says that 1 is bigger than or equal to 5 alpha, or alpha is less than or equal to 1/5. So we have two ratios here, 3/12 and 5/1, or 1/5. And which one is smaller? Well, this is 0.25, and this is 0.2. So if we increased alpha to 0.25, x2 would go negative by a little bit. So we have to, so far we're stopping at 0.2. This is as far as we can lift alpha. All right, we have 2 more to do. Let's do them a little more quickly. So x5, let's see if I can get some more room. Okay, so for the rule for x5 simply says that if we go through all the same steps, it says, oh, wait a minute, let's be more careful. This is it, because there's something different going on here. Okay, so this row says, let's see, I've lost the letters, I don't know which. Okay. So this row for x5 says, so non-basic, 0, it says minus 2 alpha plus x5, 1 times x5, non-basic 0 equals 2. So that tells us that x5 is equal to 2 plus 2 alpha. And obviously, as alpha is a positive number, there's no restriction here. So a negative number in the so-called U column underneath the entering non-basic variable has a negative number doesn't get in the way. So we can increase alpha to infinity here without forcing. So x5 is actually getting bigger when x3 gets bigger. So, but x2 and x7 are getting smaller as alpha increases. Okay, and then the last row is for x4, says what? 0, non-basic 0 says 8 alpha, the value of x3, plus x4 is equal to 4, and so that says that x4 is equal to 4 minus 8 alpha, which, to keep that bigger than or equal to 0, implies that what? Alpha is less equal 4/8, so which is 0.5. So the 0.2 is still the winner, the smallest. So all we're really doing here when all the algebra has been figured out is we're taking 3/12 versus 1/5. We're skipping this one because it's negative, and 4/8. Okay, and by the way, if we have a 0 in this spot, the same thing happens. Then the x3's value doesn't affect the basic variable at all. So the conclusion here is that what? So, as alpha increases, when it hits 0.2, x2 is equal to 0. So we know from the theory that we must have m basic variables at all times. So what we're doing here is that saying that x3 replaces x2 as basic. And in fact, in the software, so what we're doing is we've got x2 here, and we've got x3, and when we put the cursor here and hit P, it'll turn this into a 1 and put zeros everywhere else, and it will cancel. It'll remove x2 and replace it with x3 in the list of basic variables. So it recognizes the pivot step always. Anytime we hit P in the simplex method, we replace one basic variable with another. And when you do this, you'll see in the upper right corner where we have the CB transpose B inverse B, when we change capital B to have a different basic variable, it improves, gets bigger when we hit the P, because the top row is also, if we look back here, oops, if we look back here, when we pivot on this, so in this one we would pivot on this guy right here. Oops, grab a pencil. So in this one we would go right here and hit P, and it'll when it zeroes this out, that will change the value here. As it zeroes out each of these, it'll change the right-hand sides. And in fact, it could in principle change every number in the whole tableau. And the important thing is that this becomes an identity column, and the x2 column gets all muddled up, because you can see as we add multiples of this guy to all the other rows, this adds some multiple of this guy to all the other rows, and that column gets cluttered up and no longer looks like a basic column. So I think that's all I wanted to say about that. Oh, wait, we've got another problem to do. Sorry. So let me try to clean this up a little. I don't know why. Now I've lost the below part. There it is. All right, so let's go on to another page. Okay, I'm going to bring the same graphic back in. Hopefully a little quicker this time. Okay, so here's our guy. Now let's, just for fun, notice we're looking at non-basic variables. So there's 3 non-basic variables, 4 basic and 3 non-basic. And I'm ignoring Z because it's special, of course. Just sits there and doesn't really do much except to make our theory make more sense. So the x1, if we brought x1 in and tried to make it basic in place of another one of these guys, it would actually make the objective function worse. And we've seen what happens with x3, so let's look at what happens with x6. So we can streamline this. All we have to do is look at remember what we did for x3. We just computed what's called the minimum ratio. So in the software, I don't know why I'm using green. In the software, you just hit M. So if we have the cursor sitting right here and we hit M, it will move the cursor, if we have the cursor anywhere in this column, it'll move it to this row. It'll move it to the row that has the minimum ratio, M for minimum. Okay, so if we go to this column, anywhere in this column, and put the cursor there, say there, and hit M, it will flash, I think. And that flash is saying no. There is no minimum ratio. Why? Because we saw in detail on the last example with the -2 here that that does not get in the way. So in fact, none of these negative ones don't restrict increasing x6. In fact, nothing increases. So let's just to verify that clearly. That row says, so this is non-basic, 0, non-basic. So notice we're not letting x3 go up anymore. 0, 0. So it actually says 0 times alpha plus x7 equals 3. So alpha means, so a 0 in the column that we're thinking of letting enter. Oh no. The 0 in that column doesn't say anything about it. You can change x6 to any value, and x7 will just stay at 3. And when the negative means as we increase, this one means as we increase x6, x2 would get bigger and be happier, less close to being negative, which is disallowed. So this is a situation if there are no positives. That means the problem is what we call unbounded. That simply means at this point, this tableau says if we let x6 go to infinity, right along with it, all these guys will change, but the main thing is the objective function will go to infinity as x6 goes to infinity. So every unit we increase x6, the objective function will improve by 2, and there's nobody getting in the way, so that's it. So this tableau, actually all of this analysis with x3 coming in was a waste of time. I just put them both in one example to save bringing in files and stuff. Okay, so the next thing you'll be doing in the lessons is actually solving some simplex methods that are set up to go and using these simple ideas. Thanks.